300 horsepower. That's what separates winning from watching in top fuel drag racing. And in 1992, one Louisiana mechanic found that power hiding in the most unlikely place imaginable, the teeth of a pulley. Dale Armstrong didn't just break the rules. He exploited a blind spot so obvious that nobody else had even thought to look there. This is legacy motoring, and I spend way too much time thinking about the hidden engineering breakthroughs that changed motorsport forever. If you're someone who loves digging into the mechanical genius behind racing's greatest innovations, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Picture this. It's summer 1992 at a drag strip in Texas. The air is thick with nitromethane fumes that burn your eyes and claw at your throat before you've even gotten close to the starting line. Two top fuel dragsters are staged and ready. These are 8,000 horsepower machines that can accelerate from 0 to 330 miles per hour in under 4 seconds. The Christmas tree lights begin their countdown. Yellow, 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 green. Both cars launch with a violence that physically hits you in the chest from a quarter-mile away, a concussive wave of sound and heat that doesn't feel like anything you've experienced before. But something is different about one of them. The engine note is higher, angrier, like it's screaming at a frequency that shouldn't be physically possible for an internal combustion engine. That car crosses the finish line 3 full car lengths ahead. Afterward, in the pits, crew chiefs crowd around the winning engine trying to figure out what just happened. They check the blower. Standard 14 to 71 unit. They examine the fuel system. Nothing unusual. The camshaft, the headers, the clutch. Everything looks regulation. But somewhere in that aluminum maze of precision-machined parts, Dale Armstrong has hidden an advantage worth 300 horsepower, and it's sitting right there in plain sight. Nobody can see it because nobody knows what they're looking for. Here's what most is the story of how a mechanic from Louisiana outsmarted the entire NHRA rulebook with a modification so simple, so elegant, that when competitors finally discovered it, they couldn't believe they'd missed it. Armstrong didn't invent a new supercharger. He didn't discover some exotic fuel additive. He solved a problem that every single top fuel team in America was already struggling with. And he did it by borrowing technology from industrial conveyor belt. Now, to understand why that's remarkable, we need to understand the brutal physics of top fuel drag racing in the early 1990s. These weren't just fast cars. They were controlled explosions on wheels, burning through 15 gallons of nitromethane in a single quarter-mile pass. The engines operated at the absolute edge of mechanical possibility. Connecting rods stretched like taffy under load. Cylinder heads lifted off the block despite being held down by bolts torqued to 190 pound-feet. Spark plugs melted into glowing embers after a single run. The entire engine was essentially a beautifully engineered, disposable device that teams rebuilt completely between every single pass. At the heart of these monsters was the supercharger. Specifically, a Roots-type blower that could move 900 cubic feet of air per minute. And here's something that stops people cold when they first hear it. A top fuel blower consumed 900 horsepower just to turn it. Think about that for a second. The supercharger alone required more power than a NASCAR Cup engine produced in total. But it was worth every bit of that parasitic loss because that blower could cram enough air into the engine to support combustion of nitromethane at rates that would have seemed like pure science fiction just a decade earlier. Here's where Armstrong spotted the problem that everyone else had simply accepted as an unavoidable reality of the sport. The supercharger was driven by a reinforced rubber belt, essentially a giant timing belt on steroids, a massive loop of fiber-reinforced rubber with precisely machined teeth that meshed with matching pulleys on both the crankshaft and the supercharger input shaft. As teams pushed for more power through the late 1980s and into the early 1990s, they kept spinning the blowers faster and faster. More blower speed meant more air. More air meant more fuel. More fuel meant more power. Simple equation on paper. Except for one thing, the belt couldn't keep up. At 8,000 revolutions per minute blower speed, the belt was traveling at over 150 feet per second. The acceleration forces involved were so extreme, so far beyond anything the belt was originally engineered to handle, that the belt would actually slip on the pulleys. Not dramatically. We're not talking about the belt skipping teeth or squealing like something's wrong. We're talking about microseconds of slip that you couldn't see with the naked eye, couldn't hear over the engine noise, couldn't feel through the car. But those microseconds added up in ways that the dyno made brutally clear. Testing showed that at maximum load, the driven pulley, the one actually spinning the supercharger, was turning 10 to 12% slower than it should have been based purely on the drive ratio. That slip was costing teams between 300 and 400 horsepower on every single pass. And everybody knew about it. That's the part that makes this story so fascinating. The slip wasn't some secret problem that only Armstrong had identified. Every crew chief, every engine builder, every technical director in top fuel racing knew the belt was slipping. Teams had tried everything imaginable to fix it. They experimented with different belt compounds sourced from rubber manufacturers across the country. They increased belt tension until the load started snapping crankshaft snouts right at the keyway, which is an expensive and occasionally dangerous failure. They tried running multiple belts side by side. But the packaging constraints of the blower drive system made that approach basically impractical with the equipment available at the time. The industry consensus, the collective wisdom of the smartest mechanical minds in American motorsport, was that around 2,200 horsepower was about as much as you could reliably extract from these engines before belt slip became the hard limiting factor. That ceiling had become accepted truth. It was just the way things were. You worked within it, you optimized everything else you could, and you lived with the slip. That's what made Armstrong's solution so brilliant. And here's the thing that makes it genuinely elegant rather than just clever. He didn't try to fix the belt. He fixed the pulley. Armstrong's background wasn't typical for a top fuel crew chief, and that unconventional background turned out to be exactly what the sport needed. Before racing, he'd spent years working in industrial automation, designing conveyor systems for manufacturing plants. In that world, timing and synchronization aren't just performance variables, they're production-critical requirements. A conveyor belt that slips even slightly can throw off an entire assembly line, cause defects, create safety hazards, cost companies millions in downtime and rework. So industrial engineers had invested serious research and development resources into solving exactly this problem: maximum power transmission through a toothed belt drive. What they developed were specialized tooth profiles for timing belt pulleys. Profiles that provided maximum grip without creating excessive wear on either the belt or the pulley. These weren't the rounded automotive-style teeth that racing teams were using, tooth profiles that had been designed primarily for quiet operation and smooth engagement at moderate load. The industrial profiles were precisely machined with specific pressure angles and root radii engineered to mesh perfectly with the belt's teeth under heavy load, creating a mechanical interlock rather than just friction contact. One night in his shop in Louisiana, Armstrong was staring at a worn supercharger pulley, running his fingers along the polished teeth where the belt had been slipping under load. The aluminum was actually glazed, burnished to a mirror finish from the friction of thousands of slipping engagements. And that's when the connection fired in his brain. Why were they using automotive pulley profiles for something that had far more in common with an industrial conveyor system than with any car engine? The loads were industrial. The speeds were industrial. The consequences of slip were just as severe as anything you'd find in a manufacturing environment. Why wasn't anyone using industrial solutions? He pulled out his machinery's handbook, that thick Bible of mechanical engineering that sits on the shelf of every serious machinist, and started looking up specifications for industrial timing pulleys. What he found changed top fuel drag racing permanently. The standard automotive pulley tooth profile used throughout drag racing had a 20-degree pressure angle with relatively shallow tooth depth. It was designed specifically for smooth engagement and quiet operation at moderate load. Perfect for a street car. Deeply problematic for transmitting 900 horsepower through a rubber belt at 150 feet per second. Industrial timing pulleys used a 14-degree pressure angle with deeper tooth engagement, a profile that created a fundamentally different mechanical relationship between the belt and the pulley under load. The difference in those numbers might not sound significant if you're not a mechanical engineer. So here's the analogy that makes it click. Imagine trying to grip a wet rope with your fingers spread wide open versus curling your fingers around it deeply. The shallow grip might feel fine under low tension. But the moment you really load it up, your fingers slide. The deep grip locks in and holds. Armstrong was proposing to give the pulley deeper fingers. He spent 3 months in his machine shop cutting different tooth profiles and testing them systematically on a dyno. He tried 12-degree angles. He tried 16-degree angles. He varied root radii and tooth heights across dozens of combinations. Every prototype got a number and went into a notebook with detailed measurements of belt temperature, slippage percentage, and power transmission efficiency. Belt temperature was the key diagnostic tool. A belt that's slipping generates friction heat. Reduce the slip and the temperature drop. It was that simple and that measurable. The breakthrough came with prototype number 23. Armstrong had combined a 14.5-degree pressure angle with a tooth depth 15% greater than the standard racing profile and a root radius that matched the belt's tooth profile precisely under the deformed shape it took at maximum load, not the relaxed shape it had sitting on a workbench. When he ran that pulley on the dyno, the belt temperature dropped by 40 degrees Fahrenheit. That single measurement told him he'd found something real. The dyno confirmed it in horsepower terms. The supercharger was now spinning within 2% of its theoretical speed based on the drive ratio. He'd eliminated 90% of the belt slip in a single design iteration. But here's where Armstrong's genius really showed, and this is where it gets really interesting. He didn't just make one pulley. He made a matched set, both the drive pulley on the crankshaft and the driven pulley on the supercharger, with complementary profiles engineered to work together as a system. He also discovered through painful trial and error that tooth timing was absolutely critical. The pulleys had to be clocked so that the belt teeth engaged both pulleys at exactly the right phase relationship relative to each other. Get it wrong by even a single tooth position and you'd actually amplify the slippage rather than reduce it. The belt would fight itself, loading up on one side of the engagement arc and releasing on the other in a destructive harmonic pattern. Get it exactly right and the belt locked onto those pulleys like it had been welded there. The first track test happened at a private session in early 1992. Armstrong installed his custom pulleys on Kenny Bernstein's Top Fuel car, the same machine that had recently become the first to officially break the 300-mile-per-hour barrier. With standard pulleys, the engine was making 2,180 horsepower on the dyno under controlled test conditions. Armstrong swapped in his custom pulleys. Same belt, same blower, same fuel system, same everything except the pulleys. The dyno read 2,510 horsepower. Bernstein's crew thought the dyno was malfunctioning. They checked the load cell calibration. They rechecked it twice more. The numbers were real. They'd found 330 horsepower in a part that most people had never considered worth improving. Now you might be thinking, 300 horsepower on a dyno is impressive, but drag racing happens on a track. And you'd be right to push back on that, because translating dyno gains into elapsed time requires the entire car to handle the additional power correctly. The first full quarter-mile pass with Armstrong's pulleys nearly ended in catastrophe. The engine produced so much more power in the first half of the run than the team had ever experienced that it completely overwhelmed the clutch management system that had been carefully calibrated for the old power level. The car hazed the tires straight through first gear engagement, something that hadn't happened to this particular combination in over 2 years of racing. They had to start the clutch calibration process essentially from scratch, rebuilding their understanding of how the car behaved with nearly 15% more horsepower going through the drivetrain. It took 6 more test passes before they found a setup that worked. Each pass taught them something. Each pass refined their understanding of how to put the new power to the ground effectively. When they finally got it sorted, the on-track advantage was staggering in a sport decided by thousandths of a second. At the 1992 NHRA Summer Nationals, Bernstein's car was consistently 0.02 to 0.03 seconds quicker through the first half of the track than anything else in the field. That might sound small until you understand that in top fuel racing, a 0.01 second advantage over a quarter mile is considered massive. They had 3 times that in the first half of the track alone. Other crew chiefs noticed immediately. After each elimination round, competitors would walk casually past Bernstein's pit, doing the slow professional scan that racing people do when they're trying to identify someone else's advantage without looking like that's what they're doing. They checked the visible component: injector nozzles, blower intake manifold, exhaust header collector position, front wing angle. The pulleys were right there, bolted to the front of the engine, completely exposed to anyone who looked. But they looked normal enough, similar enough to standard pulleys, that nobody gave them a second glance. Armstrong was methodical about protecting the secret. He had the pulleys anodized matte black, which disguised the machining marks that a knowledgeable observer might have recognized as non-standard. He also established a strict pit protocol where the pulleys were never removed in open air when other teams were nearby. If they needed to change a belt between rounds, which was routine, the car rolled into the enclosed trailer first with the door shut before any tools came out. When rival crew chiefs asked Armstrong directly about the sudden power increase, he'd credit improvements in fuel mixture targeting and clutch modulation timing. Technically, these were things they had indeed adjusted. Technically, these adjustments did contribute to on-track performance. Technically, he wasn't lying. He was just leaving out the most important part. Here's what most people don't realize about the NHRA rulebook in 1992. It was genuinely exhaustive when it came to supercharger specifications. Page after page of requirements covering the blower case dimensions, the rotor count and configuration, the drive ratio limits, the approved materials for housing construction. The technical staff had done serious work trying to anticipate every possible avenue for gaining unfair advantage through supercharger modification. But nowhere in that entire document did it mention anything about pulley tooth profiles. The concept had simply never occurred to the people writing the rules. A pulley was a pulley. You could specify its diameter because diameter affected drive ratio, which was regulated. But the shape of the teeth? That was considered a manufacturing detail, not a performance variable worth regulating. Armstrong hadn't broken a single rule. He'd found a loophole that didn't exist in the usual sense of the word, because a loophole implies someone left a gap in protections they knew they needed. This gap existed because nobody in the history of the sport had thought to look at pulley tooth geometry as a performance variable. He hadn't exploited a weakness in the rules. He'd identified an opportunity that the rules had never imagined. For 6 months, the pulleys remained completely secret while Bernstein's team collected wins at a rate that was making other teams desperate. Don Garlits, the legendary Big Daddy of drag racing and one of the most technically sophisticated people the sport has ever produced, personally offered Armstrong $50,000 in cash for the secret. Armstrong declined politely and completely. John Force's crew chief tried a more collegial approach, framing it as a mutual technology partnership where both teams would benefit from sharing innovations. Armstrong appreciated the creativity of the pitch and still said no. He understood precisely what he had, and he understood that its value was entirely dependent on nobody else having it. The secret came out in the most mundane way possible, which is honestly how most racing secrets end. At the U.S. Nationals in Indianapolis, the sport's most prestigious event, a photographer from National Dragster magazine was shooting detailed technical photos for a feature article on top fuel engine architecture. He happened to photograph Bernstein's blower drive from a low angle with raking light that caught the pulley teeth in sharp relief. When he reviewed the images later on a light table, something looked off about the tooth profile. The geometry didn't match any automotive pulley he'd seen in 20 years of covering the sport. He showed the photos to a veteran crew chief with an industrial manufacturing background who took one look and immediately recognized what he was seeing: an industrial timing profile on a racing pulley. The crew chief made 3 phone calls that afternoon. Within 2 weeks, every serious top fuel team in the country was contacting pulley manufacturers trying to get custom profiles machined. The problem was that copying the concept without understanding the specific engineering behind it turned out to be genuinely dangerous. The pressure angle, the tooth depth, the root radius, the phase timing relationship between drive and driven pulleys. These variables had to be precisely matched to work as an integrated system. Teams that tried to reverse engineer Armstrong's approach through guesswork often made their situations worse. One prominent team experimented with an overly aggressive tooth profile that increased belt wear so dramatically that belts would stretch and slip worse than the original setup after just 2 consecutive runs. Another team's prototype pulley gripped so effectively that it overspun the blower during a dyno session, causing a catastrophic rotor contact that destroyed both the blower and significant portions of the engine surrounding it. Armstrong later revealed in interviews that his development program had cost him over $30,000 of his own money across the 3 months of testing. He destroyed dozens of belts at several $100s each. He'd scrapped at least 6 complete sets of prototype pulleys when testing revealed fundamental flaws in the designs. He'd blown up 2 complete engines when early prototypes gripped too aggressively and caused momentary blower overspeed event. One of those explosions had embedded pieces of aluminum blower housing in his shop wall with enough force that they're reportedly still there today, left as a reminder of how close the development process came to failure multiple times. But every failure taught him something. Every destroyed component told him exactly where the boundaries were. By the time he arrived at Prototype 23, he knew the failure modes as well as he knew the success conditions. The NHRA responded to the pulley revelation the way sanctioning bodies typically respond to innovations they didn't anticipate. They updated the rulebook. The 1993 regulations included, for the first time in the history of the sport, specific technical requirements for supercharger drive pulley tooth profiles. The tooth geometry, the approved materials, and even the required surface finish specifications were all codified in language that made clear exactly what was and wasn't permitted going forward. Critically, and this reflects how genuinely effective Armstrong's design was, the standardized specification that the NHRA adopted was essentially an approved version of what Armstrong had developed. The industrial-derived profile with its deeper tooth engagement became the regulated standard, not because the NHRA wanted to canonize Armstrong's work, but because testing demonstrated it was the superior design for the application. His advantage was eliminated by the rule change, but his innovation was permanently embedded in the sport's technical foundation. This is where it gets really interesting in terms of what Armstrong's breakthrough actually triggered in the broader development of top fuel technology. Once teams could reliably transmit 2,500 horsepower through the belt drive, other components that had been adequate at 2,200 horsepower suddenly became the limiting factors. Crankshafts that had served teams reliably for years started failing at the new power levels, leading to a complete re-examination of crankshaft material specifications and cross-section geometry. Harmonic dampers couldn't effectively control the increased torsional vibration signatures at higher power outputs, spurring development of tunable damper systems that had never previously existed in drag racing. Oil pumps had to be completely redesigned because the increased bearing loads created by the extra horsepower required oil pressure levels that existing pump designs simply couldn't sustain. Armstrong's pulley had essentially unlocked a door that opened onto a hallway full of more doors, each one representing an engineering constraint that had previously been hidden behind the belt slip ceiling. The cascade of development that followed throughout the 1990s was staggering in its pace and its ambition. The raw horsepower numbers tell the story in terms that are hard to argue with. In 1991, the year before Armstrong's pulleys appeared on track, the most powerful top fuel engines in competition were producing approximately 2,200 horsepower under race conditions. By 1994, with optimized pulley profiles standardized across the field and the cascading improvements they'd triggered now fully developed, teams were regularly exceeding 3,500 horsepower. By the end of the decade, 5,000 horsepower had become the competitive baseline rather than the absolute ceiling. Today's top fuel engines produce over 11,000 horsepower, a number that genuinely would have seemed like fantasy to the engineers competing in 1991. You can draw a direct line from those modern fire-breathing monsters back to a machine shop in Louisiana where a mechanic who used to design conveyor systems stayed up late running his fingers over a worn aluminum pulley and asked a question nobody else had thought to ask. There's something worth sitting with in that image. Armstrong wasn't working with exotic materials or cutting-edge simulation software. He didn't have a team of computational fluid dynamics engineers or access to a supercomputer. He had a machinery's handbook, a manual mill, a dyno, and the patience to run 23 iterations of a design while carefully documenting every result. The tool that unlocked 300 horsepower wasn't a computer or a wind tunnel. It was a different perspective, one shaped by solving similar problems in an entirely different context. That cross-domain insight, the ability to recognize that a problem you're facing in one field has already been solved in another field, is genuinely rare in highly specialized technical communities. Racing teams in the early 1990s were staffed almost entirely by people who had grown up in racing, who had learned their craft from other racing people, whose entire technical vocabulary was shaped by the specific problems and solutions of motorsport. Armstrong's years in industrial automation gave him a library of solutions that racing engineers had never encountered because they'd never needed to. When he looked at a slipping blower belt, he didn't just see a racing problem. He saw a synchronization and power transmission problem. And he knew exactly where to look for solutions to that category of problem, because he'd spent years in an industry where that category of problem was the central engineering challenge. Now, you might be thinking that this is an interesting historical story, but what does it actually mean for how we think about motorsport engineering and innovation today? Here's what I think is genuinely important. Armstrong's story is not really about pulleys. It's about the relationship between domain expertise, fresh perspective, and the invisible assumptions that accumulate inside any highly specialized community over time. Every form of motorsport has its Dale Armstrong moments waiting to happen. There are assumptions baked into current engineering practice that seem as obvious and inevitable as belt slip seemed in 1991, assumptions that will look just as short-sighted in retrospect once someone from outside the traditional talent pipeline looks at them with different eyes. The question is never whether those opportunities exist. They always do. The question is who has the combination of outsider perspective and deep enough technical credibility to identify them and then execute on them effectively enough to produce a real advantage. Armstrong had both. His industrial background gave him the perspective. His time in racing gave him the credibility and the specific knowledge of what the problem actually was and what constraints any solution had to satisfy. Neither piece alone would have been sufficient. The industrial engineer without racing knowledge wouldn't have known that belt slip was the specific problem to solve or understood the packaging and operating environment constraints. The career racing engineer without industrial background wouldn't have had the reference library of solutions that made the answer visible. Armstrong retired from Top Fuel racing in 2014 after a career that spanned decades and included stints with some of the most successful teams in the sport's history. His pulleys, in their modernized form using aerospace-grade aluminum alloys and surface treatments that weren't commercially available in 1992, are still spinning on drag strips all over the world every weekend. The basic tooth profile, that 14.5-degree pressure angle with deep tooth engagement that emerged from prototype number 23 in a Louisiana machine shop, remains largely unchanged from Armstrong's original design. Not because nobody's tried to improve it, but because he got it essentially right the first time. In interviews after his retirement, Armstrong was asked repeatedly whether he regretted not patenting the pulley design, not finding some legal mechanism to protect the financial value of the innovation and extract ongoing compensation from the teams that adopted it. He consistently dismissed the question. By the time patent protection would have been in place, he said, everyone in racing would already have their own version. The real value was never in the specific geometry of the teeth. The real value was in understanding the mechanical principle that made the geometry matter, because once you understood the principle, you could apply the same thinking to any toothed drive system in any context. Find where the loss is occurring. Understand its root mechanical cause. Engineer a solution based on first principles rather than convention. Test systematically, document everything, and don't accept the first result that seems good enough. Keep pushing until you understand not just that something works but precisely why it works and exactly where its limits are. It sounds straightforward when you write it out that way. But as Armstrong's story demonstrates, straightforward principles applied with genuine rigor and the right background perspective can produce results that look like magic to everyone who's been staring at the same problem without fresh eyes. The next time you watch a Top Fuel car launch from the starting line, that moment of biblical violence where 11,000 horsepower translates into a force that moves a 2,300-pound car to 100 miles per hour in under a second, remember that somewhere in that blur of mechanical intensity, the drive pulleys are spinning with tooth profiles that trace their lineage directly to a Louisiana conveyor system engineer who asked why racing was using the wrong pulley and then spent 3 months and $30,000 of his own money proving he was right. He didn't outsmart the rulebook by being sneaky. He outsmarted an entire industry's accumulated assumptions by being curious, rigorous, and willing to look somewhere nobody else had thought to look. The biggest performance gain in Top Fuel history at that point was hiding in plain sight, in a component everyone touched every single day without ever really seeing it. Sometimes that's exactly where the breakthroughs live. In the parts you've stopped questioning because they've always been good enough. Armstrong stopped accepting good enough and found something extraordinary. What's the most clever racing innovation you've ever heard of? Drop it in the comments below because I read every single one of them. And if this kind of deep dive into the engineering brilliance hiding inside motorsport history is what you're here for, subscribe and stay close, because we are just getting started.